With the LMS algorithm, our goal is to solve the Wiener-Hopf equation using gradient descent. That's what we've been talking about in the last few lectures. But we're going to deal with a very practical question of how do we get Ry and Rdy in this process? Well, to lay some groundwork, I want to first describe why it's called the LMS algorithm. The LMS algorithm comes from the fact that we are trying to minimize over our weight vector the expected value of the error squared as a function of time. So least it comes from the minimization. Squared comes from the fact that we are squaring the error. And mean comes from the fact that we're taking an expectation. Least mean squared. Next, I'm going to do a slight change of notation. Due to the example that we had in an earlier lecture where we were actually trying to predict symbols that were transmitted through some system where the input was perhaps X, the output of our RF channel was then Y, I'm going to switch to saying that the input to our filter is X. And that's primarily because it's a more general case. I don't know why it is, but for some reason in DSP we often call the input to a system X and the output Y. So to be consistent with that, we're going to change notation, but I hope it won't throw anybody off too much. As before, we have D being our desired vector. W is a column vector of our filter weights, and X is also a column vector of the same size as W, having the most recent samples of the input signal X, which we denote with lowercase x. Although we've already solved for the optimal estimator here, we're going to go through the steps again and make a few different choices along the way to facilitate the computation of our weight updates and our adaptive filter, as it were. So we'll start back with minimizing the expected error. We will perform the same gradient calculation that we did before. We've already gone through this a little bit. We're going to go part way through the same computation that we did before, pausing right here at 2 e of n times delta w of e of n, which we found was equal to minus 2 times the expected value of the error times the input vector. Now, as you recall, at this point we can substitute in an expression for E, which is right there above, circled in green, and carry out the expectation, and we get our normal equations. But instead, we're going to skip that step and move directly over to our gradient descent approach. In the gradient descent, we have that W sub L, like L better than I, plus 1 is equal to L minus 1/2 mu times the gradient of the expected value E squared n. And of course, we've just calculated that up above, yielding this expression here. So this is going to be the basis of our LMS algorithm. But one major question remains, and that is, how do we estimate this? Recall with our previous gradient descent explorations, we could calculate this quantity, the expectation, based on the autocorrelation matrix and the cross correlation between D and our input. This time we're going to take a different approach, and we're going to try to calculate or estimate this quantity directly. So, what are some possibilities? This first approach would be to simply average the last capital N products of the error times x of the associated input, and recall that this error would have to be calculated as dk minus W transpose x of k. Another approach would be to use some sort of recursive averaging. This might make life a little bit easier. So in that case, we would have that our estimated expected value was equal to 1 minus alpha n plus 1 times the sum from the beginning now of alpha n minus 1 ek x of k. So that should be alpha n minus k. 0 less than alpha less than 1. We could actually implement this using a simple single pole recursive filter. Well, for now, we're going to focus on this first method up here. And we just have one question left, and that is, how large does n need to be to make this useful? We're actually going to, for the LMS adaptive filter, make the shocking decision that n is equal to 1. So it goes without saying, but I'll say it anyway. That's a terrible way to estimate an expectation, to simply take a single value and call that the expected value. But there we go. That's our first, I would say, crazy approximation that we're going to make as we develop the LMS algorithm. The second one is also going to be a little bit crazy, and that is that as we do our multiple steps in our gradient search for the optimal solution, we'll actually stop after one step. I'll explain further how this works. Okay, so using our approach, we now have this iteration to get our optimal filter, and we've approximated now our expectation that's required in this with a simple sample. So we have two issues here. The first one is, you notice that we have indices of L on W. Those indices represent the gradient steps. We have indices of N on X and E. Those indices represent time. So I'm going to change this around just a little bit, and we'll add both indices, L plus 1 at time N is equal to WL at time N plus mu E, and I'm going to add an L in there, and then finally an X, and I'll explain why in just a moment. There we go. It's possible that this optimal adaptive filter can change now as a function of time. And indeed, the way we've implemented it, it's going to end up doing so. So that means that our error is going to be dependent on which filter is being used to calculate the output. So we've added the indice in L on our error term. And also we've added the time index to show what's going on there. So the LMS algorithm now makes one last big approximation that I alluded to a moment ago. And that is, what if we tied the time index to the iteration index? Then we would do only a single iteration on our gradient step at each time index, and everything simplifies down a bit. So we have, where we had WL plus 1 at time N, we're only ever going to have a single iteration, so that just becomes W1 at time N. And we're going to combine, that'll be our last one, so that quantity will become the filter at time N plus 1. So now we can finally write our LMS filter weight update. So the first thing you'll notice is that there are no matrix multiplications, matrix inversions, matrix operations of any kind. The only vector-vector operation is used in calculating our error, and it's the same operation that is used in calculating the output of our filter, so that's a necessary step of filtering anyway. Beyond that, we have a vector addition and a scalar multiplication, scalar by vector. So this becomes a very simple algorithm. So I want to illustrate kind of conceptually what this is doing compared to what we've talked about so far. If we were to plot our error on the y-axis and time, or increasing n, on the x-axis, with standard optimal solutions, we would get data in, and we would iterate to the optimal solution. Or we could skip the iterations altogether, and we could solve the normal equation, and when a new sample came in, we would just immediately come down to our optimal solution, and our error would be very small. Well, the LMS algorithm is going to do a single iteration, or a single step, and then it's going to move on to the next sample. So with the LMS algorithm, the error is going to do this. Sample 2, when we calculate the output there, the error is smaller. Now if we were doing some sort of, if we could actually calculate the expectations, we might be able to once again come down here and calculate our new outcome. But that depends on, or we could just use our previous filter as before. Why would we do one over the other? Well, we would redo the iterations if we had a new Rx and our correlation matrix and a new cross correlation, in which case we could redo our iteration steps and come down to the optimal solution yet again. LMS is content to just move in that general direction, but as time goes on, it's going to eventually make it down to the optimal solution. But it won't get there until some time has passed, because with each new sample, we are taking a single step. Now here's another way of thinking about that. Over time, our weights are going to accumulate mu times en x of n for different values of n. If mu is very small, this is effectively averaging the product of the error and x, which is what we had planned to do to begin with when we decided to take the easy way out and average only a single sample. So over time, we're now effectively calculating or estimating something akin to our expected value of en times x of n. But in the process, not only have we generated eventually our optimal weights, but the filter is running the whole time. And so we're able to have this thing running concurrently. Our estimator of the optimal filter weights is running concurrently with the filter and producing admittedly inferior results at the beginning, but as time goes on, the results get good. And we now have a very efficient filter that is easy to calculate, easy to implement, and appropriate for implementing in real-time systems. One other point is that in this case, E of n is calculated with W of n. So every error term is calculated with a different set of W weights, because these weights have been updated over time. So our initial error is going to be large, and as we go on, the error becomes smaller and smaller. But it is only the most recent version of the error that is actually used in updating the weights. The averaging is more of a conceptual averaging, and so we end up getting something that makes sense in the large, but when you look at it very closely, we'll find that proving convergence is a little bit trickier. We'll do that in a later lecture. For now, let's look at a summary of the entire LMS algorithm. There are essentially three steps. The first is to calculate the filter output. The second excuse me, is to calculate the error. And the third is to update our filter weights. And we've just spent time with that equation, so it should be a little bit more familiar. So this is the entire basic LMS update. And this equation, or these three equations rather, can be implemented in just a few lines of code. In MATLAB, 2 to 3 lines, depending on how you combine terms, and in C, just a few more, with loops to loop through the individual weight values on the updates and the calculating the output. So one of the things we'll be spending some time with a little bit later is how to set this up. Where do we get D from, for example? And if we have D, why on earth do we need to estimate it? We'll talk about a variety of situations in which we can set it up so that we have a target D and that the estimator filter is very valuable. But here's one example, just so you don't have to wait forever. What if you had an unknown system? You could excite it with some input. Maybe you want to get the room response of a concert hall. So your input might be noise that you would play from some position, maybe up on the stage, and you would measure the room response to different spots in the audience hall. So that unknown system would be your measurement at that spot in the audience hall, or wherever it is that you might measure the output of an unknown system. And you would now let this adapt. When you're all done, W would now equal the response of our unknown system. So this is a very good and common way of doing system identification. As I say, we'll talk about some more methods later, but in our next lecture we're now going to have to spend some time figuring out, does this converge? We know that under certain conditions our gradient search converged, but we just made enough approximations that that analysis is probably not, it's going to be needful to revisit that.